Hello, everyone. Welcome to the fourth webinar for 2025. My name is John Bagiliko, a PhD student at the University of Rwanda, and also at African Institute for Mathematical Sciences. I'm also a core team member of the AfriClimate AI community, and I am the lead for this seminar series. So just to give a small intro about AfriClimate AI. So we aim to create a vibrant community of students, researchers, professionals, and policymakers who collaborate, innovate, and drive forward the development and application of AI to support regional and continental climate change mitigation and adaptation strategies. So we do run several projects and activities, and one of them is the AfriNet initiative, which seeks to set up low-cost automatic weather stations across the continent and develop data APIs that would significantly bolster the continent's capacity for accurate and localized climate data collection. We also have the benchmarking project, and its goal is to create a comprehensive framework for evaluating weather forecasting models over Africa, focusing on baseline data sets and performance. And this seminar series is one of the activities that we run. This is to promote knowledge sharing and collaboration within the community. So today we have Ezéckiel, who is a student at the Pan-African University in Kenya, and he specializes in stochastic environmental modeling, hydrological forecasting, and AI augmented hybrid modeling frameworks. He has a strong background in mathematics, probabilistic modeling, and numerical simulation. He also focuses on leveraging non-Gaussian physics-based models and integrating machine learning techniques to better understand and predict complex rainfall runoff systems. His recent research centers on developing a hybrid framework that combines stochastic hydrological models with machine learning to improve rainfall runoff simulations in data-scarce and highly variable regions. He applies his innovative methods to African river basins, such as the Yala River in Kenya and the Ouémé Basin in Benin. Driven by a passion for interdisciplinary research, Ezéckiel seeks to bridge theory and practice to advance sustainable water resource management, enhance climate resilience, and support risk assessment across Africa. So before he starts, if you are not muted, kindly do so that we don't have interruptions while he's presenting. If you have questions, kindly note them down, and once it's done, he would take them. You can put them in the chat and we will read them after, or once it's done, you'll be allowed to unmute to ask them directly. Without much ado, I would give Ezéckiel the floor. Ezéckiel, the floor is yours.
Okay, thank you, John, and hello, everyone. First of all, I have to thank all the AfriClimate AI founder for allowing me to present our work, which is about hybridization of stochastic hydrological models and machine learning methods for improving rainfall-runoff modeling. So, sorry, this is just the content of my presentation in short. Before we start, we need to talk about what we mean by rainfall-runoff transformation. So it is just a process by which water flows in a river or a stream after there is rain, after it rains. So as we can see here on the picture, anytime you have precipitation that comes from atmosphere, like simply I can say anytime we have rains, we have three main possibilities for that water that flow or on the land. The first possibility is, or the first main possibility is what we call infiltration, which is a process by which water seeps into soil. Another one is what we call evapotranspiration. And evapotranspiration normally mean, in that words, we have two different words. We have transpiration and also evaporation. So transpiration is, as you can see on the picture, it's just a process by which water is removed by trees. And when it comes to evaporation, we have the sun that normally removes water. So all that phenomena together is called evapotranspiration. So compute that variable. So that is one of the variable in a rainfall-runoff system. So the third possibility of the water is that the remaining water is supposed to flow over the land. And then all that mechanism combined together generate what we call runoff. And as I said at the beginning, runoff is just the amount or the level of water that is generated and that flows in rivers after we have rainfall. Now, why is it important? Modeling rainfall runoff system is like focusing the level of water that flows in a river after it rains. It is very important because of so many reasons. And the most important, the biggest reason is the anticipation or assessment of extreme event risk. When we talk about floods and drought, those two phenomena are climate-related events that really affect the whole world. And it is very interesting to develop more advanced approaches that can be used to anticipate that event in order to conserve the environment and to also to prevent that kind of situation in the case where they will come normally and affect the society. It is also important because it helps for an efficient management of water resources. Also, it is very important because it helps to design infrastructure such as dams, reservoirs, and drainage system. Also important because it helps to assess the effect of land use and climate change on water availability. It's also important because it helps to conserve the environment. If I can say, last year, by the same time here in Kenya, we had water everywhere. And what about the regions where there are rivers? That region, that's the situation that we got last year here. It is just an example I'm giving. Was even crazier in that region. So this kind of modeling can help normally if we can be able to predict over time for so many days. It can help to prevent that situation and to know that we can be able to expect in advance that kind of situation. In hydrological modeling, or simply in rainfall runoff modeling, models normally are categorized into three different classes. And as you can see, we have three different classes. The first class is what we call conceptual models. And those models, you can see some example as I have provided. Conceptual models are just models that are based on empirical relationship between different variables, either they are climatic variables or hydraulic or physical variables. After that, we have physical-based models. And for example, we have soil and SWOT, which is soil and water assessment tool, and HyMoLAP also, which is a physical-based model. Now, physical-based models use physical laws, such as momentum principle or energy principle. And the last class of model in rainfall-runoff system is what model that we call empirical or data-driven models. Those models are just statistical or time series model or machine learning models. And the difference between empirical or data-driven models and the other models is that empirical models only learn statistical pattern from data. They don't need to explicitly determine the relationship between the different variables. No, they just learn statistical relationship between the different variables in order to generate runoff. For any rainfall runoff model, we need to know that there are some inputs that are used, and that inputs are normally what impose normally the dynamic of runoff that we generate from that models. And that input can be categorized into 3 different classes. We have a class of climatic input, hydrological input, and also physical input. Rainfall and temperature are just climatic input. Evapotranspiration can be classified as a mix or a combination of climatic input and also hydrological input. And even soil moisture is also hydrological input, and long dews normally is a physical input. So any hydrological model use especially climatic data to simulate runoff after we have precipitation. Now, what is the difference between deterministic and stochastic models? Very important. If you have a model and for the same input of your model that you give to your model, you generate different outputs after so many runs. You need to know that that model is simply a stochastic model. So there is what we call randomness that is included in that model. That is why for the same inputs, you have different outputs. So when it comes to uncertainty, deterministic models don't include uncertainty, but they explicitly include stochasticity. Now, it is very complex to simulate stochastic model than deterministic model. As I was saying, some method to simulate stochastic model is one of the methods that we can use to simulate stochastic model is what we call Monte Carlo simulation. And the moment you are running your deterministic model just once, sometimes you can even run more than 10,000 your stochastic model. So it is very complex to simulate a stochastic model as well as a stochastic system than a deterministic system. The key challenge, there are so many challenges in hydrological rainfall runoff modeling. And this modeling this system is very complicated because of so many reasons. And the biggest reason is the first one that, as you can see here, the impact of climate change. Yeah, we can say that the impact of climate change 5 years ago is the same as what we are having today. Even there, you can even see in literature that there are so many models that even work perfectly before, and nowadays that model are not really working because of the kind of data that we have, because of the complexity that we have between the different variables in hydrological or rainfall runoff system. We also have the non-linearity of the different processes. Also, we have the data availability. Data availability, it is there are some models, they need a lot of variables, as you can see. But Now, if you don't have a lot of the data or all that variables, you cannot even simulate that model. Now, data availability is something that is very important. Data, you need a lot of data in order even to select or even to learn the relationship between that data in order to generate runoff. So I know that some countries in Africa, we have especially that issue. Sometimes we want to use some different model or advanced model that include a lot of variables, but because of data, we are short in doing that. And also we have what we call uncertainty in the model input. This is even related to the way data are measured. If we take like precipitation is the most important variable, the most important input data in rainfall runoff system. And once that variable is not well measured, it will be very complicated for model to well represent the rainfall runoff system. So that is what we just mean by uncertainty in model input. So apart from that, we also have the lack of data for extreme events. If you take any hydrological or runoff data, we have what we call low discharge. Discharge is also, it is the same term as runoff. If you say runoff, we are also saying discharge as well as streamfall. So it is the same thing we are trying to say like that. Now, when you have your runoff data, the low values determine what we call or can normally help to understand drought characteristic, and the high values represents flood situation or flash flood situation. Flood situation is just like rapid flood situation. Now, AI came in the field of hydrology, for a lot of reasons, but the main reason why we can talk about here is the fact that AI came, and for rainfall runoff system, that models can be able to simulate runoff based on different input data. It was shown in 2019 by a researcher from Germany that LSTM, long short-term memory, which is a neural network architecture, can be used to simulate rainfall runoff system. But before you get very good result with that kind of model, with AI, you need a lot of variables as input in order to better learn the relationship between all the variables that exist or that influence the runoff. So after that, so many researchers also found many ways to incorporate AI into existing process-based model. And by doing that, they try to combine the advantages of both approaches or both methodologies in order to improve this representation of rainfall runoff system. And we have two common ways to do that. The two main ways to create hybrid model that combine hydrological model and AI are, as you can see here, error prediction. Error prediction, in a simple way, you can take it as when you have your hydrological model that you use to simulate your system, and then you compute the error that you will now predict using AI models. After that, we have another approach that is the incorporation of hydrological models output as inputs for AI models. And this can be, sometimes some people, they take it as what we call physics-informed neural network, but it doesn't normally follow the classical definition of physics-informed neural network, because for physics-informed neural network, you need to include your physical equation into the loss function of your neural network architecture. But in this case, yeah, it is true that we are also giving physical information to our machine learning model, but the way we do it is different. That way to do it is just to use the output. No, it is not working. Okay. Sorry. The way we do it is just that we use the outputs of the physical models that we include, that we use now as input for the machine learning model. It can also be a combination of observed data and also that output from the hydrological model. Now, after, or even before this work, I'm presenting all the method that exists only use deterministic hydrological model. So it was found that we can extend that approach to stochastic hydrological model. And by doing that, we were able to get some interesting results that we will present in this work. So basically, we had 3 different objectives. And the first one is to develop the hybrid models that integrate stochastic hydrological models with machine learning methods in order to improve the system simulation. The second one is to assess the performance. And before assessing the performance, you need some data. So we use data from Ouémé at Bonou. It is a river basin data, a river basin from in Benin. So after that, because we are dealing with stochastic model and we are going to get output from stochastic model that we use as input for the machine learning models, we need to analyze the range of uncertainty, the consideration, the how that will affect our hybrid model. That is part of what we call sensitive analysis of our formulation. Now, this is just briefly the introduction. You can see we can go directly to the methodology. And before we start, we need to talk about the data that we use. So basically here we have the model that we use only use 2 data to generate the third one, which is the runoff. Okay. Now, the 2 data sets that we use are just precipitation data, which is, as I said before, is the climatic data, and the potential evapotranspiration data, which is normally can be seen as climatic data or a combination of climatic and hydrological data. Now, from that data that you can see in black, we will be able to use different models to simulate or to generate the third data that we have here, which is supposed to be something that will be complex, as you know, because even the structure of the last data is really is very different from what we have for the precipitation and also for the evapotranspiration data. But there are some models that I normally use to do that. Now, the model that we used for our formulation is a stochastic model, but that stochastic model was formulated based on a deterministic model. The deterministic model that we use is just the model that we call hydrological model based on the least action principle, HyMoLAP. And that model was created by a researcher from Benin in 2010. No, sorry, in 2010. Now, the model is just a differential equation, an ordinary differential equation, as you can see in equation 1. The capital Q is the runoff data or the runoff variable. We have here the small q, which is what we call effective precipitation. Like it is just the maximum of the precipitation minus potential evapotranspiration and 0. And S of t is the variable that describe the soil humidity, or in another term we say soil moisture. So that S of T verify the equation 2. Now we, based on that equation 1, and then included the last term, sorry, as you can see in the equation 3. That last term is what is bringing now the randomness in the system. The last term that you can see here in blue, yes, here, is it is a multiplicative noise, as you can see. The L of T is a Levy stable motion, which is, those who know Brownian motion can also know this, but because they are playing almost the same role there, but the only difference is just that for Brownian motion, the distribution is a normal distribution, but here it is a distribution that we call alpha stable Levy distribution. So we were able to formulate the model in equation 3. This formulation can see in, it is the same, we are the same author who did this in our previous work before this work that we have here. So I'm not going to really talk about how we formulated this model, but if anyone is interested in that, we can get in touch after the presentation. Now, in short, the equation 1 is an ordinary differential equation, which is a deterministic model, and the equation 3 is a stochastic differential equation, which is a stochastic model. And the difference is that the main difference is when for the same input for the first model, we will get the same output, but for our equation 3, for the same input, you will always get a different output, and that can be solved using different methods such as Euler-Maruya method, or even, yeah, there are some methods that can be used to solve this equation. And from that equation, sorry, I'm taking a lot of time here because I think it is very important to explain better what we are going to. Because of this term, we also simulated the model using finally what we call, there is a technique we call Monte Carlo simulation, because that can help to estimate the probability density function of each day, yeah, of runoff for each day. That is the approach that we use for output generation from that stochastic model. Now, we tried a lot of machine learning methods. I can't say a lot, but some of them, especially SVM, random forest, LSTM, gated recurrent unit that we call GRU, and also HGBoost. But finally, we only retain just 2 of them, this one that we have here and the one that we have here also, the gated recurrent units. Now, we choose these 2 because of some reason. Actually, this provided better results, yeah, than SVM and random forest in our formulation. This model is just a model that can be trained by optimizing the equation 3, which is the loss function, or the optimal function to be minimized. L of y that you see there is a loss function that can be even computed using statistical metrics such as error, R, MSE. And the R that we have here is the regularization term that is here to avoid what we call overfitting, and C is just a constant. After that, we have here the gated recurrent unit. This is a variant of LSTM model, as I was saying before. Normally, RNN, recurrent neural network models, are built for sequential data. They can be in form of image or time series data. Now, the problem that they got is what we call vanishing gradient, and it was because of that problem that LSTM was created in order to solve that issue. And finally, LSTM really solved the issue. But the issue that LSTM got itself is the computational cost, which is very expensive. That is where gated recurrent unit came in 2014. And this is very cheap when it's very cheaper than LSTM in terms of computational cost. And we use this in our work because it is true, it gave a similar result to LSTM, but we use it in our work because of the reason that I just said. The fact that it is cheaper in terms of computational cost, as we've got a lot of simulation to do in our work. After you get the output of the stochastic model, before we went to the machine learning model, we did what we call wavelet transformation. This is just a pre-processing technique that's used to remove noise from data. And we have different kinds of wavelet transformation. We have what we call discrete wavelet transformation, continuous wavelet transformation, and also stationary wavelet transformation. But the most widely used is wavelet transformation is what we have here, which is the discrete wavelet transform that we also use in our study. It is defined by the equation 5, and normally it is characterized by so many parameters with too many parameters. And by combining that too many parameters that we call decomposition level and model wavelet, we're able to identify the best decomposition that really work in our framework. Now, after presenting all that different models separately, we have here this formulation of the hybrid models. It is just simple to understand. We have just 3 main steps here. What we have in yellow here are just the data, but in green, you can see that the main step of the formulation. I suppose your model, you have the input. In our case, we only have 2 inputs as model inputs. But for any stochastic hydrological model or any stochastic given any other field, you can have so many input data. Now, after your input data, getting your input data, you can simulate your stochastic model using Monte Carlo simulation approach. And by doing that, in order to get unique value for every day, you will get a set of value. And from that set of value, by using Monte Carlo simulation, you can be able now to compute the average trajectory or so many statistics such as standard deviation trajectory, variance trajectory, quantile trajectory, even correlation trajectory. You can be able to simulate that from your stochastic model for each day. You see, you generate that values for each day, and then you use all the time series that you have generated to build the trajectories. And after getting the trajectories, you do what? You apply the wavelet transformation to that trajectory in order to remove noise from the data, and also to better prepare your data or your new data that you have simulated from the stochastic model. Now that can be ready to be used as input data for your machine learning model. And this is just the structure of our formulated hybrid models. Now, after you have any model, when you have any model, you need to assess the performance of that model in order to check if your model is working well or not. And in hydrological modeling, the most widely used metric is what they call Nash metric, NSE, which is the first one, and the optimal value is 1. And after that, we also use other statistical, so many statistical metrics such as R square, RMSE, MAE, and CA. CA is a combined accuracy, which is just a combination of 3 different metrics: R square, RMSE, and MAE. So the optimal value of the CE is 0. We have this is the first result of the simulation after formulating the model. Now, the result that we have here, we are not yet simulating the hybrid model that we formulated. This is just the normal simulation, like you use the observed data as input and you simulate your HyMoLAP model. Sorry. So by doing this, you can see that, okay, for the first year, the runoff generation is not bad, but the second year, it is not that good. That is why even the scatter plot, you can see that the dots are really scattered. They are dispersed from the as y equal to x. Now, you see what we got here, NSE and CA. The NSE, we said that the optimal value is 1. So the objective is to get a value of NSE that is close to 1. In that case, we can say that our model is perfect. And a CA value that is very small. Now, this is the normal simulation using the observe input as input for the HyMoLAP model. After that, we also did the same thing with the machine learning models. You can see that here, the machine learning model didn't give any good result. The results are not interesting. Even what is surprising here is that they grew for us when we even implemented the standalone machine learning model. We were even thinking that the neural network model would gave better result than the WXGBoost model, but it was the opposite because, as you can see here, for the GRU, the NSE is very small, which is not at all interesting. Even the CA is even greater than 100. So the result that we have here from the standalone machine learning models are not that good. And it can also be observed from the scatter plot, as you can see here. Now, we can just move ahead. This is now the preparation before this hybrid formulation. What we have here is some output that we got from the stochastic model. Using Monte Carlo simulation approach, we were able to compute different trajectories. The red one is it is a bit confused to the orange one, but it is normally the average trajectory. That is just the mean trajectory. Like you compute the mean for each day that we use now as trajectory. Now the 1% quantile is in green, and we also have the 99% quantile, and the difference between the two quantile. We can even plot more than that, like standard deviation, variance, and other statistics that can be computed. But here we only use that 4 trajectories as inputs for the hybrid model formulation. We try to consider two input data scenario. The first input data scenario is when we only consider the average trajectory as input data for the hybrid model. Like you simulate your stochastic model now using observed data, and then the result that you get, you only use the average trajectory, which is normally confused to the deterministic result that we got from the HyMoLAP model. And using that average trajectory, we simulated each of the model, HG-boosting model and also GRU model. As you can see here, the case of HG-boosting model didn't improve the result of the standalone HyMoLAP model, but it is only GRU who provided improvement. It is something that also surprised us because when we used the standalone machine learning models, we found out that the GRU model provided the lowest accuracy. But when it's come now to the hybrid formulation, in the first scenario, we consider the GRU-based hybrid model is giving the best results here in this case. Now, in the second scenario, you can see very good improvement here for both first year and second year. And the scatter plot of both of them can even show what we are talking about. As you can see, in this input data scenario, we have improvement of both hybrid models, especially the second one, the GRU-based hybrid model gave a very significant improvement compared to the standalone machine learning and also hydrological models. Now you have some key results here concerning the performance of the different models, both standalone models and also hybrid framework. Now we can say we have 4 different hybrid models if we try to consider the 2 input data scenario. And it is only in the case of average trajectory as input data for the machine learning that we don't have improvement when we use HG boosting model. So it means that the 2 scenario improve the results. The GRU model improve the result for the 2 scenario. But it is only for the second scenario where we use so many input data that the HG boosting hybrid model normally improve the result. And as you can see in red here, the improvement result is interesting. We have over 7%, like 7.3% as improvement when we compare the result to this hydrological model, HyMoLAP. And when we compare the result to the machine learning model, we can see that the improvement is very big, especially when we compare to the GRU we compare the result to the standalone GRU model. Now, when the same observation is also made when we try to use the CA as evaluation metric. We got very significant reduction in terms of the combined accuracy, which is very interesting. Now, this is the overall performance of the model. So it can be seen that we have a very good performance when we evaluated the models using the whole time series. Now, if you take someone who is working in hydraulical field, any hydrologist, and you tell that person that you have your hydraulical model that is simulating runoff, he will ask you, is that model able to well simulate extreme events? Why? She need to ask because extreme events here are defined by low and high runoff values, and that low and high runoff values determine what we call draft and flood. I can say it again. The low runoff values determine draft, and the high discharge values determine flood. And once you have your rainfall-runoff model, in order to better assess the performance of that model, you need to evaluate the capability of that model to simulate extreme situations that are extreme, that are draft and flood. And that is what we did here. Let me zoom a bit. As you can see, we use different models here. As you can see here, we try to divide the time series that we have into 3 different categories. And the first one is the runoff values that are less than 25th percentile. The third one is the values that are greater than 75th percentile. So the first one is just the low values, okay? And the last one is the category of the high values. The other ones is the medium values. And for the hybrid formulation, you can see the last model that gave the overall best performance also gives here the best performance when it's come to low and high discharge simulation. As you can see here, we have 10, not 10, 12 as RMC, which is the error. The goal is to have the smaller RMC for each class, but that is what we are getting. The lowest value of RMC is normally got by the stochastic HyMoLAP-WGRU model. And also similar observation was made when it comes to the high discharge value. So it means that in addition to simulating all the first, we know that our model is our hybrid model are able to better simulate overall to better simulate the runoff simulation compared to the standalone model. And in addition to that, the models are also able to better simulate extreme event data draft and flood situation, which is very interesting. That is just what I wanted to show here. And this is the analysis, sensitive analysis of the uncertainty range. Here, we only need to know that this analysis was conducted because we wanted to show that not all output from the stochastic model can be relevant for the hybrid formulation. You know, I remember we tried some output like even in this case here, when we use the first scenario, the average trajectory, we didn't see that in the first case of HG boosting model, we got improvement. We didn't get improvement. Yes. So it is similar thing I'm going to show here. In the case of HG boost hybrid model here, you can see that at the beginning, when the quantile level is equal to 0, the performance of the model was very, very, very low. It was not that good, as you can see. It means that when you consider the extreme quantile, like 0% and 100% quantile, you see that you consider the full range of uncertainty as input for your hybrid framework. And in that case, we didn't have good results here, as you can see. But by reducing a bit and trying to get close to the median, we see that the result was better until we got the best result in terms of the accuracy for both approaches. But it can be seen that with time, we also decrease I can say we decrease only for the HG-boost hybrid model here. So it means that the growth is better in our formulation as it shows normally more stability compared to the HG boosting model here. So it means simply that if you want to adapt the same framework for any kind of system, you need to try so many input scenario. Yeah. Like you can, because it is a Monte Carlo simulation, so you can be able to simulate a lot of trajectory, any kind of trajectory that you want as statistical property. And by testing a lot of that trajectory, you can be able to find out, according to your system that you have, the best input data or the best output data from the stochastic model that will be used as input for the machine learning model. And then this is something that is very interesting because there is no universal model that can be able to simulate any kind of rainfall-runoff system. There is no that model. So sometimes you can find a model now that works normally for a system A and then use the same model for the system B, and that model will not work. This is how this modeling works normally. So you need to try a lot of input scenario in order to find out which one are better for your system that you are modeling. Now, in short, we need to understand that this presentation or this work provided a new techniques of integrating stochastic model, hydrological model with machine learning by only using precipitation and potential evapotranspiration data without even depending on previously observed discharge data. And the result indicated that the standalone machine learning models provided the lowest accuracy in when we only use that to input data as first data, which are observed data also. And the GRU-based approach provided the best results in our formulation, meaning that the GRU approach or the GRU model is better, shows some stability, and also is better for our formulation in maybe in this kind of rainfall-runoff system, but it can also be different from any other rainfall-runoff system. We also need to note that the input data must also depend on the system, as not all of the input data that we use were able to provide improvement compared to the standalone machine learning models. Now, this formulation now we work only use HGBoosting and also LSTM and GRU, but we also some advanced approaches that are LSTM Allo, LSTM Info, LSTM IM, RFO, and so on. That also can be that models can be also used to test normally the performance of this framework when it's come to model any other hydrological system. So it is just a framework, but can still be improved. Even can be the framework can be extended to uncertainty quantification by using Bayesian approaches. There are some approaches today that we can even go Bayesian neural network. And instead of using maybe GRU, here you can use Bayesian GRU or Bayesian LSTM. And by doing that, you can provide uncertainty quantification, which should be like, instead of predicting just unique value, as we did here, you will just predict a set of value, which should be like interval prediction. So I think this is, in short, what I have to present. And these are just some references that we use in our work. And thank you for your attention. Your question, welcome. Thank you.
Thank you very much, Ezéckiel. This is very interesting, and it contributes to the field of runoff simulation. Are there any questions from the audience? You can raise your hand and ask, or you put the question in the chat and we'll read it to the speaker. In the meantime, Ezéckiel, I have a question. So where you are simulating the extreme events, I mean, where you are evaluating the modules for the extreme events, I see that you used the 25th percentile and then the 75th percentile.
Okay.
However, other people suggest that for extreme weather events like this, you are looking at 5th percentile and the 95th percentile. Did you check how the model perform on those as well? Otherwise, what's the choice for the 25th and 75th?
I think this is a good question. And normally it depends on the data that you have or the characteristic of data that you have before deciding about the percentage to take as low discharge and also high discharge value. But in our case, we just try to see. Actually, we saw that values under 25th percent are very low. But I can say that we just assume that, okay? We just assume that based on the characteristic of the data that we had, because we got a lot of low data, and also it is true that the maximum data are not that a lot compared to the low data. But normally, from practical work, I think it will be interesting to go deeper into this analysis in order to know which percentage to take in order to better represent that event.
Okay.
Okay.
There's a question in the chat that could you go back to your model structure page, and that
Okay.
you would like to know more about the hydrological model outputs and which
Yeah.
variables are used as inputs.
Yeah.
I think so. Tao, can you unmute and better ask the question if you can? Okay, but in the meantime, he's saying which variables are used as input for the ML model.
Yeah. For the standalone machine learning model, we use precipitation and potential evapotranspiration. That is where we got the result that we have here, as you can see. Only the observed data that we have, precipitation and potential evapotranspiration data. And that is what we got. Okay. So now when we use the simulated result from the stochastic model, we did the same thing, and this is what we got. That is the difference between the two cases. I don't know if
Okay, can you go back there? So the P dot PET, what that's the precipitation? What that's
yeah, P is observed precipitation.
precipitation?
PET is potential evapotranspiration data.
Okay, and then we move to the second stage, which is a Monte Carlo simulation.
Simulation, yes. And
So
then
first of all, the first step is daily data, right? The P and PET are all daily data. And
exactly,
then you do the simulation, and it also gives you daily data, but each day you have a range of values.
exactly, exactly,
Okay,
exactly.
okay.
Mhm.
And then you go to the other part.
Of machine learning.
So then you do the wavelet on those set of data.
Yes.
And what does it give you once you do the wavelet? What's the structure? How does it, is it
Um,
still daily and averaged?
yeah, no, it is just daily, the same data, but the structure is a bit different. That's why I was saying, like, I was saying that it is a pre-processing technique that normally remove noise from data. So it only have to transform your data, but it's still the same structure, like daily data.
Okay,
Okay.
okay, good. Tao, I hope you got that. There's also a question from Wisdom who says, have you tested your models with different data sets with different characteristics, missing data, different
Yeah.
extremes,
Um,
seasonality, and so on?
I tested with data from Kenya here, one of the basin in Kenya. You know, the weather condition in Kenya here is very complicated than in my country, Benin. So it is they are different, but I can say that data I use, there were no missing data, but the structure, when it's come to seasonality, even the trend is, it is different. And I also got improvements when I apply the same approach using that. So only, I wanted to show to also like apply to that basin in the paper, but with after talking with my supervisor, they said no, just one uh, river is okay for the formulation. That is why we don't have it. But it normally works for another set of data with different structure. That's we
Okay.
similar case.
Okay. There's a hand from Orel, but before he asks, Tao says, what are QU and QV? I think from the
Oh,
third
okay.
the input. Yeah. What
This
are they?
okay, quantile. Like what we have here, we have 1%,
Oh,
99% quantile difference. I think we have more explanation about that in the paper.
okay.
Yeah.
So Tao, you can see the details in the paper. So Aurel, go ahead and unmute yourself, please.
Okay, thank you. Hi, Ezéckiel. Thank you for the wonderful presentation. I wanted to ask what actually makes the model hybrid? I don't know if I got it right. It seems you are predicting the simulation results from the hydrological model. I don't know if I'm correct. You can correct if I'm wrong. I wanted to understand if the machine learning algorithms are actually helping the hydrological model to predict, or, I mean, you can explain. And the second question is about the data. Have you used recent data from Benin as well? Because I think the data used is from before 2010. So the climate has changed a lot from then to now. So do you at least plan to test the models on recent data? Thank you.
Okay, thank you. You too. About the first question, let me go back here. This is what is done normally. This is what makes the model formulation as hybrid formulation. You have your stochastic model that you simulate, and then you use the output from that stochastic model to inform your machine learning model by just like the output from the stochastic model become now input for your machine learning model. And that is why this process is called hybrid framework. Is it okay?
Yeah, so what is the output of the hydrological model here? Is it also predicting the runoff?
Yeah, these are the output, as you can see, because it is stochastic model. So it's like you simulate your stochastic model, hydrological model, and you get a different value for the same day. Now you can be able to compute statistical properties of using Monte Carlo simulation. Okay, like the mean trajectory, the mean value, the mean, the quantile, standard deviation, variance, and so on. That we will use now for all the day together to build your different trajectory as new data for your machine learning models. Is it
Yeah,
clear?
not really. What's the difference between the two models? And so if I'm correct, it's like the hydrological model is outputting a distribution, and you use that as input for the machine learning model. But what is that predicting then? Is it like the true observed value for, let's say, the true prediction, or like how
Yeah.
models, like, I didn't really get how the models are communicating with each other.
Okay. If I can answer your question, I suppose that you have your machine learning models, okay, and you have your observed data. Now you use your observed data, you train your machine learning models, right? And you get an output.
Yeah.
Is it okay?
Yes.
Now, for the hybrid formulation, instead of using the observed data, you only use, okay, in our case, you can even combine, but in our case, we only use the result that we got from the stochastic model as input data now. It is like you are using the stochastic model to generate data now that will be used as input data for the machine learning model. Is it okay?
Yeah. So the machine learning models have never seen the rainfall, the precipitation data.
No, nothing.
So they have only access to the Monte Carlo simulations
Exactly.
generated by the hydrological model.
Exactly.
And they're predicting from then the discharge.
Yes.
Okay. Thank you. So what about the second question?
Yeah, I think you are right about the second question. We only tested using this data, which is from 2006. Honestly, I didn't get new data, like data for recent years in this case. You understand? But I use data from 2016 to 2020, I think 21 in the case here for Kenya. You understand? To also test the approach using different hydrological conditions. So as I said, I also got some improvement. It is so that the improvement that we have here in the case of Benin is greater than what we got when we used the case of Kenya. But yeah, if I can answer your question. I didn't get recent data for Benin. Is it
Yeah.
okay?
Thank you. Anyways, this is an amazing job. Well done.
Thank you. Thank you.
Ezéckiel, if I can just ask a follow-up. So, which years did you use for the training of the model? And
Okay, it
the
is here
test?
4 years for the training and 2 years for the testing.
Okay. So the graph you are showing after the I'm seeing it's all run from 2000.
No, I didn't show, we don't have here the training result. We only have the result
Okay.
of
Yeah, you are
test.
only showing the test, which is what, yeah, of course.
Yeah, yeah.
Okay. Cool.
Okay.
By the way, you have a compliment on the chat, that great study and great talk. Thanks. I just noticed that the study is published from Tao. Randani, please go ahead.
Thanks so much, Ezéckiel. This is quite interesting work. Actually, I don't actually have a significant question. It was perhaps leading from the previous question about more data from Benin. We have worked as well on the same similar basins, about 10 of them in Benin, and we actually have a few data sets that go until, if I'm correct, just around 2020. So it could be interesting to even just test the models in that particular data set. So we're happy to share those with you. But yeah, again, I find this quite interesting. Maybe another sort of interest in terms of how you would scale this, because I think this could work quite a lot in sort of flood risk management. Would it be interesting to scale it to other data sets like Caravan that have discharge data, and you can overlay that, I guess, with the precip and potential evapotranspiration data sets that you have? Would it be possible to sort of like, again, scale it to as many basins as possible using data sets such as Caravan or
Yeah, sorry, I didn't get the question well. I don't know if you can repeat it.
Oh yes, I was just saying, is it in terms of your next steps? Okay, the other one was just offering you data, so that's fine. And then the other one is if your thoughts on scaling this to other basins on the continent to start with, maybe using open source data sets on discharge.
Okay.
Ezéckiel, did you get the question?
No, I didn't
So,
get it.
so
I'm just trying to-
whether you plan to scale it to other basins on the continent, given you have data, is that?
Okay, like this is like the question that's Tao asked, right? Like if it can be able to work using different data sets. Is it that?
Okay.
Yeah, I think
So
that's fine. Yeah, so
basically,
we can send you an email about the data that we have in Benin, and perhaps if we could use other sort of gauged basins that that are on the continent.
Okay.
and then there's a question from Mashadi.
Okay.
Besides standalone ML models, did you try any time series models for the base case? And if so, what were the results looking like?
Okay, but you are talking about what we got here, right?
Well, he says that
Mhm.
put aside the the standalone ML models. Did you try other like time series models? There are models
Um,
just for time
no, no,
series.
we tried like only machine learning model. Like apart from these two models that we use here, we also tried random forest, SVM, and LSTM. LSTM gave similar result to GRU, but random forest and SVM didn't provide better result once for our hybrid formulation.
Sure.
Okay.
And I don't think there's any other hand. Okay. So there is no question again. Okay. Thank you very much, Ezéckiel, for making the time to present your work to the community. This is very interesting. And we hope that, once you have other future works, you will be happy to present it to the community as well. Um, so that should be it for today. We will see you next month. And by the way, once you are here and you have any work that you wish to present to the community, kindly reach out to us.
Okay.
And I mean the audience, and we'll be happy to have you share your work with the community. Thank you very much, everyone, for joining the seminar. Have a good evening and a happy May Day tomorrow.
Thank you. Thank you.
Okay.